So, I believe I'm live. And with that, hi guys, and welcome back to Brain-Friendly Thinking. I hope my mic is working this time around. It seems it is. And cool. Wonderful. As we're waiting for people to arrive, I just would like to start, as in the last couple of times, with a quick recap of last week on the show. What did I do last week? Last week I started off with an ABC list for a topic I called natural action. A natural action meaning how do we act in a natural world. I came up with a couple of words based on my ABC list, such as action, costs, mental model, and that's of course what I'm trying to develop. Noise, the objective, that is the objective of the action I'm taking, and so on. Noise means noise in perception, it means noise in action, and so on and so forth. After that, I categorized those words, and then I, for a very long time, tried to somehow look at how these things are related. We have the objective leads to the action, there's noise that intercepts the translation from objective to action, and so on and so forth. So yeah, and then I went into the whole rabbit hole of memory, and that memory could be potentially a bottleneck, and I went over some studies related to expertise that shows that experts don't have a higher memory, but in their area of expertise they can remember more because they have a certain structure. And I speculated that this memory bottleneck could be due to sensory overload, and this was specifically in patients with peripheral nerve repair. That means a cut due to injury and subsequent repair of the hand nerves, because that's what I looked at for my PhD. Yeah, maybe the sensations were too noisy. But the important thing is that last time I was not I was sort of thinking this is going in the right direction, but how do I actually make this concrete on a very, let's say, on a very conceptual way. I know what I want to say, I know the objective. There's something missing here. The objective is translated into action, but you also need perception for that, and the perception is noisy. Anyway, the question is, how can we actually make this more concrete? And just this week, I found a paper. I'm not going to go through the whole paper with you, but I would like to show you something that I think I haven't showed on this channel before, and that might be quite important, or not quite, but quite a lot of people might find this useful. So first, let me take my notes from last time, and I'm actually going to first show you the paper. So this is the paper. It's by Matthias Schultheis, Dominik Straub, and Konstantin Rodkov. All of them from the Technical University of Darmstadt. It's about inverse optimal control adapted to the noise characteristics of human sensory motor system, which is quite a mouthful. But I think essentially they're doing something similar to what I'm trying to do. They're trying to essentially see how can sensory motor system essentially means the it includes the sensation, the perception, but it also includes the action, so that we actually move something with our motor system. And we got noise in there. So they are proposing a computational model that takes noise into account and that can explain the performance of the sensory motor system. Blah. As I said, I'm not going to go through the whole paper, but I would like to go through some of the formulae here. I would like to show you what I'm doing to understand what these formulae are doing. How I basically, you can think of that as decoding the formulae. I'm not sure how best to describe it, but essentially a formula or an equation is really a very condensed way of storing knowledge. And there's either some logic behind it, or there's some data behind it, or there is some more elaborate model behind it that is expressed by that equation. And in order to understand the equation and be able to use it later on, not just for some of the exam questions or the exercises, but actually use it in a real context, you need to understand what is this equation is trying to, or this formula is trying to encode. And so you need to decode it so that later on when you look at that, all this decoding is part of your memory. Okay, so, and there's some very nice formulae, some very advanced formulae. I'm not going to go through all of that today, but I would like to go through some of that. So how do what do I do when I try to decode this? Jesus, certainly not this. Go down, go down, go down. There we are. Okay, let's first see what the authors are saying. We model a human subject as an agent in a partially observable environment, as introduced by Todorov. I don't know him or her. That's something to read later, and depicted in figure 1a. What is figure 1a? So this is figure 1a. Let's see, what do we see here? I think this is not quite big enough. There is zoom. Okay. Figure 1, the agent experimental loop in its formalization, it's POMDP, whatever that stands for, together with the inference problem from agent point of view and from the experimental point of view. But we're specifically talking about figure 1a. And here we have some variable x at time t. And from that we get a variable x at the next time point and then at the next time point. And in order to get this, we sort of need to do several things. I don't know what yt is yet, or x bar t, or ut, but apparently all of them influence what the next x is going to be. And I'm guessing, I don't know it, but I'm guessing that x is the state of, it's either the state of the world, I guess, I'm guessing. Or, well, I'm guessing because I read some of their other papers and I'm also started reading this paper. It's either the state of the world, or it is the state of the agent in the world. And every time we seem to, I'm not sure whether this is a measurement. Let's call this a measurement for now. We're taking a measurement, and then we are computing something, but this something is not only dependent on what we are currently measuring, if this is a measurement, it's also dependent on what we computed before. So this is the model they are trying to put into maths. Good. Okay, oops, I scrolled. I need to scroll a little. Wonderful. I need to scroll a little bit higher. There we go, that's better. Okay, so we model a human subject as an agent in a partially observable environment. Okay, this is actually important, this partially observable environment. That means we don't really know what the environment actually is like. So let me switch to my desk view and say partially observable environment. Let me try to capture this or decode this with a CaGa. Let's say we have a head here. This is the nose. Is that, oops, this might not be big enough for you, and it's certainly not in focus, but I think you can see the head here. Here is the nose, here is the eye, this is the neck. Great, and we are observing the world. So let's say we're looking, this is supposed to indicate that this person is looking at the world, but the world is only partially observable. So let's say there's a tree, and the tree is actually here, but I can only see part of the tree. I can only see the part of the tree that's up here. I can't see what's down here. So it's only partially observable. I could also, this time the person looks the other way. I can also think about other potentials. So if we again have our tree, and this time I would see more of the tree actually. However, this might be partially blocked by something else that's in the way. And then only, let's say, this part here again is observable. So we have only a partially observable world. That's at least how I understand what they mean. Okay. For this we consider a discrete time linear dynamical system with, okay, wonderful. So we have a lot to decode here. And whether you read this very fluently or you think, what on earth, oh sorry, I need to getting used to OBS, switch back to paper. And whether you think, what on earth does that mean, or whether that has some semblance of meaning to you, depends on what you know. Discrete time means that we have discrete time steps. So usually we think about time as linear. That means between time point A and time point B, you can have infinitely many. That means you can have a, sorry, I'm trying to express that in plain English, but I realized that I'm not very good at that because I haven't done so very often yet. Let me actually switch back to the drawing board and try to express that again as a CaGa. This here is the arrow of time. Of course, it starts somewhere in the past. We are currently here. This is the future. Wonderful. Now, if you take our current time point and you take any other time point, usually we think that there are many, many, many time points in between. In fact, there is an infinite amount of time points in between. No matter how close to the current moment we choose a time, there will still be an infinite amount of time points in between this point and the other. This is continuous time. But discrete time, on the other hand, is we have one time point here, and then we have another time point here, and another time point here, and there is absolutely nothing, zero zilch in between. It's sort of like, usually if we observe a clock ticking, tuck, 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 time will have happened between the ticks of the clock. But in a discrete time, we're just assuming between one tick of the clock and the next tick of the clock, no time has passed. Time only passes when the clock ticks. Yeah, maybe on second thought this wasn't such a good idea anyway. But let's continue with this paper and see whether I can make some sense, that it makes some sense to me and also hopefully makes some sense to you. And maybe I will fail miserably, but that's part of the fun. So we're talking about a discrete time system. That means we're assuming that time is not continuous but happens in concrete chunks. And the reason why we're assuming that is not because it does, but because it makes the math easier. We have a linear dynamical system. Okay, so we have a dynamical system, a system that changes between time points, but it changes linearly. And I'm guessing in this case, linear simply means we have a linear function. This is an area of maths I'm also not so familiar with, but I'm assuming we have a linear function rather than a quadratic, or in this case exponential, I guess, or a square root or whatever. So if this here is time and this here is action response, which might be I'm reaching forward to grasp something, or I'm turning my head, I'm doing so linearly. Yeah, they said linearly, not continuous. So, okay. Already we see we have certain things which we need to decode, but we have the state xt. Okay, what does this mean? Xt element r to the m and control ut element. Okay, so this is essentially a shorthand, and it's if you're not used to it, it's really confusing, but it's mathematicians and people who are using maths, like theoretical physicists, theoretical engineers, simulation engineers and physicists and all of that, applied mathematicians, they really like to be concise and really terse and express what they have to express in as few signs as possible. So we had, can you see that? Okay, yes, xt, and then this very funny looking e, and then r to the m. Now t, the subscript t usually denotes time, and it actually told us what it is because it is the state of this whole discrete time linear dynamical system. Whatever state of a system might mean, but essentially this is something, x is something about the system that you can describe. Here actually I should write this in bigger so you can see that better. This is already the first formula, if you like, that we need to describe. In this case it's a logical formula, it's not a computational formula, but we need to decode this. And the way I like to do this, sorry, let me get my pens that I have lying around everywhere. Okay, so what I do is, and I use several colors for that. You don't strictly need to do this, it just, where you will see in a moment, while I think this is a little bit more organized. But you don't need to do it if you don't want to. So I circle this, sometimes I just underline it or do sort of a semicircle, and then a little squiggly line or straight line, and then I say this is the world state. Great. Can you read this okay? I hope. And this thing here, and you might not be familiar with this, but if you've done a little bit more advanced physics, then you know this subscript T usually indicates a time point. Not always, it can stand for other things, but in this case it's a time point. Specifically, if we have a, let me use this color here. Here I said these are our discrete time bins, and we just call one of them T. It is just, this is just a convention. You could call it T1, sometimes you see it as, or T0, sometimes you see it as, actually yeah, let's better call it T0. Then the next time point would be T1, the next time point would be T2, and so on and so forth. So this is maybe at 0 seconds, 1 second, 2 seconds. This could be at 0 seconds, 3 seconds, 6 seconds. It could also be 0 seconds or 0 hours, 1 hour, 2 hours, 0 days, 1 day, 2 day, whatever the time frame is you're looking at. And so T can be T0, T1, T2. And the way we usually do this is the first T gets a T, and then the next one is the T plus 1, T plus 2, and this one could be, does not necessarily need to be T0, maybe later we want to talk about T2, and then the next one is T plus 1, which would be T3, T plus 2, which would be T4, and so on and so forth. Great. This, now we come to this funny looking E that almost looks like a euro sign without the second line and without crossing over. It is just a very small or very concise way of writing is an element of. Can you sort of almost read this? Sorry, let me try to make that a tiny bit bigger. Is that legible now? Yeah. Yeah, I think now it's sort of legible. Okay. So, this is the world state at a specific time point. What the world state is, we don't know yet, but let's get there little by little. And this is element of R to the M. R, did I write this correctly? Let me quickly check. Rm, yes. So that usually means that this is a real number. And if I understand this correctly, it's not just one real number, but it is actually m real numbers. Oops. What does that mean? That means that we essentially have something like a vector. If we think about, let's continue with the example here. I could, for instance, measure the angle of, if this is the axis of my head, and this is the axis of my field of vision, I could measure the angle between the two. Let's call this theta. What theta? Theta, maybe A for altitude. This is something I could measure, and this would be a number, a real number. Also, I can measure other things, and I don't say that this is necessarily what needs to be measured, but I can measure other things. If this time we're looking from overhead, this is the same person, and we have our tree here, so he or she is looking again at the tree. I can measure another angle, so I can say that the axis of the tree and my head, and sorry, let me also draw that. If this is, these are the shoulders, so I can say if this is the axis of the shoulders, there's another angle I can measure. Let's call this theta, what T for turning, I don't know, might be a bit confusing. This T and that T is not the same, or TW, whatever you want to call it. And that would be another real number. So we have in this case two angles, which are two real numbers, and they would tell me about the state of the world at time t. If I'm moving, if this person is turning his head, for instance, and the angle changes, or tilts its head up and down, the angle changes, then the state of the world would be describable by two new real numbers. But it's still two new, it's m numbers means a finite amount of numbers. Maybe it is 1, maybe it's 2, maybe it's 10, maybe it's 10,000. But it is some finite amount of measurements that I need to take, and then I can estimate the state of the world. Estimate, by the way, not completely know it, because as the paper says, we have a partially observable environment. So what does that mean? What does partially observable mean? Well, it means there's some uncertainty, there's some noise. And this is exactly where I want to get at. I want to see how can I take this noise into account. Great. So let me use another color and say what is the world state, and this time an arrow. That would be a vector of sorts. Okay, and this is essentially how we decoded this now, and then we can move on. Great, and we have a control, ut. This is rp, so this is essentially exactly the same. Ut is also a vector, which you, by the way, can also see because it is printed in boldface at time t, and it is element of another array of real numbers. In this case, p, because not necessarily the same. It's not necessarily the same number of controls. So let's see. Let's try to depict this in a CaGa again. This is the state of the world. Now I want a control state. What the control state would be, for instance, what do I need to do? Well, it actually means what do I need to do to change the state of the world. And in this case, well, if I really want to change the state of the world, it might be pushing the tree. I'm not sure whether the tree is the best analogy here. But you could imagine that if I draw this little guy again, a little bit bigger, from the top with the two shoulders here, and now I also draw his or her arm. Is that an arm? There's a sort of an arm that's supposed to be an arm with a hand here. I could be measuring, for instance. Let's keep the coloring consistent. Apologies. Let's keep the coloring consistent, and I could, where we have two, the arm should really come from here, right? Anyway, we have two muscles here. This is one muscle, this is another muscle, and the same here. We have one muscle and we have another muscle. Cool. Let's label them muscle 1 and 1, muscle 2, muscle 3 and muscle 4. Then I could say, well, I could measure how relaxed or contracted the muscles need to be, and then I can write something like M1 is equal to, and here we have another number, which is U1. Then the second muscle has a different type of contraction, U2. M3 has a different type of contraction, U3. And M4 has a different type of contraction, U4. Okay? And this is essentially my vector. So in this example, we would have used 2 real numbers to describe the world state and 4 real numbers to describe the action I'm going to take. That's at least how I understand this paper. Or control, they call it control. It's essentially what I can control, with both control independent and control dependent noise. Okay, and now comes, and let me draw this first. Now comes the first formula, the first equation that is also difficult for me to decode. So the first thing I need to do would be, I copy it first. So we have, and let me write this big enough so you can see it as well. CT plus 1 is equal to AXT plus BUT plus V. What's the name of that Greek letter again? Is that psi, or I can't remember? Or is that an epsilon? Anyway, another Greek letter, T, plus sigma. No, that's epsilon, right? I'm too bad with my Greek alphabet, sorry. C, I, U, T. Okay, this is more complicated to decode. Let's try to do it anyway. So first of all, we have xt plus 1. What is xt plus 1? This is the state of the world at time t plus 1. So you can also say at next time point. So essentially we are given a couple of inputs, a couple of vectors at a certain time point, and we want to calculate one of those vectors at the next time point. That's what xt plus 1 means, and we said before, yeah, x might be, I don't know, the angle I'm looking at, So we have a certain number of real numbers. And then this one here, this is exactly what we've been looking at before. This one here would be the state of the world at current time point. Right, okay, so the state of the world at the next time points depends on the current state of the world. That is already reassuring, that makes sense. However, we have this A here, and that means the state of the world is somehow transformed, and I don't know yet what the A means exactly, but we will find out. Then we have u of t, and what was u? U was the control variable. So in my example that I made, I said if you reach with your arm, then I drew in 4 muscles, M1, M2, M3, M4, and the contraction of each muscle, that shows you how you control your the input, the control input, in order to make a reaching movement. So this one would be the control. I don't want to call it control variables, but let's call it, what shall we call it? Let's call it the control parameters. That's a good word. That's a nice word. That sounds scientific. And again, we're not only taking the state of the world from the last time point and the control parameters from the last time point and add them together, but we need to somehow transform it with this b here. And again, I don't know yet what this b is. We will find out. I also don't know what this v, xi, or whatever this Greek letter here means. And here we have a sum, so we're adding things together. And I also don't know any of those, except these are also our control parameters. Actually, I should say at current time. Cool. So we're starting to decode. We're starting to decode. The formula doesn't make total sense yet, but it starts to make some sense. And that's the important point. That's what we're trying to achieve. We're trying to slowly worm our way in and find out what the formula means. Okay, oops, but before I do that, I need to go back to paper. Great. So let's now see what the other things mean. Okay, we have this. I really should look at what this value is here. What's the, if I just search for that, what does it tell me? It is xi, yes, not the xi. So, okay, xi, t, e, r, m. And I guess epsilon t to the i, e, r are standard Gaussian random vectors and variables, respectively. Okay, there's again a lot to unpack here. Cool. So, first of all, we see something similar from what we have seen before. And let me write this. If I go to the desk, so we had x of t, we had u of t, and now let me quickly write xi of t, xi of t element r m. This is actually one of our noises. Again, we can measure it by a set of real numbers, 1 real number, 2, 3, 4, 5, and it seems the same number of real numbers as for the world state. which makes sense because each of the variables by which we measure the world is associated with an error term, and that seems to be here. So essentially this is the state of the world plus the error term. That's how I read this. And does the paper say more on this? Does the paper say more on this? The variables resulting in control independent noise with covariant V transpose noise, and control dependent noise having covariant blah, blah, blah. Okay. So okay. What I can see from that. So both this part here and this part here is the noise. And it appears to me, oh, that's the wrong color. It appears to me, they call it the control independent noise. The control independent noise. What that means is, no matter what you do, your measurements of the state of the world will always be noisy, and this is the term that measures this noise. It's again a vector, so these two should map. For each measurement you take as part of this vector here. Oh yeah, that's maybe something important to say. It said something about Gaussian. What did they exactly say? They are standard Gaussian random vectors and variables. That's a very nice word. Okay, what does that mean? What color should I choose? Can you read this? If this is a coordinate system, this sort of bell curve is a random distribution. This is supposed to be a bell curve. I just can't draw. And this distribution has a mean somewhere. And all the points to the right and the left, if I had drawn it correctly, there would be as many points to the right of the mean as there are to the left of the mean. So if you draw randomly, you're just as likely to draw this one as you are to draw this one, as long as they are equal distance from the mean of the distribution. And so this Gaussian vector means a certain type of noise, a completely random noise. Essentially, how can I draw this? I could draw it here. If this is a line, this is the real line. It's supposed to be a straight line. And if you have random noise, then you have a lot of wiggling around this line. And the important bit is some of that. The important bit is if you were to count each spike here and draw it on a distribution, you would get certain spikes, especially in this case a lot of small spikes, of which you would get very many, so they would be close to the mean. And in this case, the mean would be the line, so 0. And some of the spikes are a little bit above. Let's say this direction. This direction to the right is above this line here, and that direction down here is below the line. So there are a lot of little wiggles that are just a tiny bit above the line or a tiny bit below the line, and the wiggles that are actually way above the line or way below the line, there are not very many of those. And so if we say this line is the true thing, but this squiggly line, the straight line is the true thing, the true state of the world, but the squiggly line is what we can actually perceive. Not because the line is really squiggly, but because our perception is noisy. This is exactly what the authors are trying to model with this term here, and this is why it's Gaussian. That means the wiggle around the real thing doesn't have any direction. Does that make sense? I don't know. I hope it makes sense to me, but if you... At first, when I heard the term Gaussian noise, I had no idea what that meant, and it's very likely that my explanation also doesn't make a lot of sense. So let's say this is Gaussian noise. Cool, I'm decoding that. I'm at the next stage of decoding, and this is, by the way, why I use different colors. You don't need to, you can do everything in one color if you want, but it just, for me, it makes it visually clearer to see on which level am I. So in this case I use turquoise for the actual formula, for the equation, and then the first level of annotation I use orange, then the next one I use green, then I might use red or purple or whatever, but it's just, it looks more organized to me, and looking at that, it makes it easier for me to read this. Again, you might be different. I don't claim this is the only way of doing it. Cool, so with that, let's look back at our paper and see what else we can get. So we have psi of t is another vector. That means for every measurement you take of the world, you have a noise term associated with it. Right. Okay, and then we have this sum here. And this is what they call the control-dependent noise. What does that mean? Well, not only is our measurement of the world noisy, if this is, again, this is the straight line, we can only perceive the squiggly line even though it's a straight line, but also our action. If I'm reaching for this line, I will not end up exactly where I intend to end up. I might undershoot the line a little bit, I might overshoot it a little bit, land a little bit too far to the right, a little bit too far to the left, and that is also noise. And so this whole term here to the right appears to be control-dependent noise. I don't know, why do they sum it up? I don't know that. Why do they sum it up? Having covariance. So C, or this A, B, V, C, they are quite clearly some form of transformation. But why do they so let's see, what are they doing? So first of all, let me draw another circle around this and say this one here is control dependent noise, and essentially they're taking this control term here, so essentially that tells me how I should dial my control parameters. This ut was the control parameters at time t, and you multiply it with a noise term, but not with the noise vector. You multiply it, then of course you transform it, you multiply it, and there are several of these control dependent noises per time, and you add all of that up. I don't know why. Let me finish this thing off here. I still don't know exactly where these values come from, but they are some form of transformation. That means sorry, I also need to draw this. that so if we forget about all of that, let's try to explain and express in plain English what that means. Let's forget all of the other terms. It means the state of the world and the next time point depends on the state of the world of this time point, but it is transformed in some way. It's not exactly the same as it is now. And this is this A. In case you know linear algebra, this should be a matrix. Again, if we forget about all the other terms, what this means is that the state of the world also depends on my control action that I'm taking. If I'm trying to push this pen, where it is in the next time point depends on what control action I actually took. And again, there's a transformation here because it is not exactly the action I take, but you need to transform it to see how did this wiping of my hand impact the rolling of the pen. And then again you have, that's the thing. So I want to know where is the pen located on the paper. And in order to know this, I need to look at that. But there's noise associated with it. We don't realize it consciously because our brain is very good at filtering that out. There is, however, a certain uncertainty. Sometimes, if I make this very blurry, yeah, something like that, if I make it very blurry like that, so if I were to take off my glasses, well, even then it's not as blurry as in the picture right now, but even if I take off my glasses, then it's it's less clear where is the edge of this pen, where's the exact position of this pen. So here I have a lot of noise. If I tune the, okay, now it's back in focus, and now it's much clearer to see. And this is expressed by this term here, which would mean that the state of, if I leave out everything there is here, it would mean that the state of the world depends on the noise of my perception. In the next time point, it depends on the noise of my perception at this time point, at the current time, which doesn't make sense, but these two things go together. So it depends on, this is the real vector. This is how I understand it at the moment. Maybe I need to fine-tune this later, but my current understanding is that this is the real state of the world right now, and if I add this noise component together, they tell me what the they tell me how I perceive the location of the object in the world or the state of the world. So let me try to rewrite this. This is an assumption, a speculation, but from what I decoded so far, it makes sense. Let's give that some other variable that is not used. I think then, let me just check. I don't think they're using Z in there. They have X, Y, U, X bar. Yes, I don't think they have Z or A or anything like that. So let me give a new variable and call it Z, and say Z would be equal to, or actually it's Z of t, would be equal to X of t plus psi of t. And then I could say that Z is my perception of the state of the world x of t is the real state of the world and psi of t is the perceptual noise. So take the real state of the world, add to that the perceptual noise, and you arrive at my perception of the state of the world. Great, awesome. So I still don't understand why they do it like this here. Maybe later. For now, yeah, for now I just need to accept this. The agent receives an observation y of t. That is part of another vector. What's that? From the observation model. Okay. And here we have another formula we need to decode. And just looking at this already looks kinda almost sort of not completely unlike the one before. We again have a transformation. We have the state of the world. Not sure what omega is. Let's write this down and see what we get. Let's see what we get. So we have y of t is equal to h xt plus w omega t plus again some form of sum I is equal to 1 ETI di and x of t. Getting smaller and smaller. So I can immediately decode some of the things that you can see here. For instance, I know what x of t is, and that's the same as the one here. X of t is the state of the world. For instance, the position of the pen or the position of the tree, as we had before. So we have the state of the world state. What was y of t? Let's also look at that. Y of t, that was somewhere in that figure. Is y of t our internal response? Did they say something above here? Okay, this is the observation. Fine. Wonderful. And then it says omega t is again a noise term. And this one here again standard Gaussian. So we again have two. So the covariance of the state dependent observation. All matrices of linear dynamical system can in principle. Okay. So this is an observation, and I think at current time, and I think this is quite similar to what I call the Z of t. Or maybe it isn't. So anyway, we have our noise terms again. And this one here seems to be the same as that one there. So is that control dependent noise? That doesn't make a lot of sense. But this one here is definitely noise and noise again. And then here we have some form of transformation. So we have some form of transformation again. So for instance, the position of the pen is translated into an observation of the pen, which depends on where in the world is the pen located. It makes sense that ideally our observation depends on that. But also how noisy is this measure? So they're using they're using omega here and psi here, which indicates that they are not the same thing. This is observational noise, this is noise in the real world. Oh, interesting. Interesting. I don't know yet what exactly the difference between the two is, but they are definitely Gaussian as well. But yes, something is slowly starting to make sense. Essentially, I need to be able to transform. I need to be able to transform the, let's call it the real position. In this case, if we use the pen as an example again, the real position of the pen into some form of vector. And I don't need to do it in an abstract coordinate system, but in my own system. And then I can add to this the noise term. Okay. This makes a little bit more sense, or it gets into how to actually take into account the noise. Let me go back over what I've done a long time ago. Yes. So essentially what that means is, if I want to model that mathematically, at least using this optimal control theory that they're using, very long time ago, which means a few weeks, I guess, back in the old year, I had the example of I'm being touched, which deforms my skin. This deformation of the skin can be measured in forms of a vector. This is then translated into a nerve signal, and the nerve signal depends on the noise. So the deformation of my skin is noisy, and so I can say, if I want to predict the signal that is being sent on, I essentially take the real pressure. So I take the that's the real state of the world. I take the shape of the pen, or the cap in this case. I take the pressure with which I press. That gives me one vector, one set of measurements. To that then I need to add the noise of the receptor cells, and that gives me an estimate of what the next stage of the processing pipelines receives. And then they will transform it in a way, but there is a noise added there as well, and that gives me another way of, or that gives me the prediction for the next step. And these formulae here, they are a way of modeling this, of expressing that mathematically. Okay, we're not there yet. I'm not there yet, definitely. But I hope it gave you some idea of how you can take a very difficult formula, very difficult equation, and decode it, essentially. Because, as you can see, all of those symbols, they mean something. They mean something individually, and they mean something together. Now, you might need to read up more to understand it if you don't know what a Gaussian noise means, and I didn't know that half a year ago. Or yeah, we have now almost February, a little bit more, like 8-9 months ago, I didn't know what Gaussian noise is. You read up on this, you try to understand it, you try to translate it, you say, okay, what happens with this, what happens with that, and then you slowly, little by little, decode this formula. And you might tell me that takes a very long time, and I don't disagree with you. It does take a long time, but the thing is, now this one formula takes a long time. The next similar formula you see in the same field, in the same according to the same topic, takes much less time to decode. And one of the reasons why I could decode it so fluently today, comparatively fluently, is because, as I said, 8-9 months ago, I read another paper which already talked about this with a slightly different framework, but trying to do similar things. And a lot of the decoding, like what on earth is Gaussian noise? And okay, this is the states, there's a state vector and there's an error term, and okay, they're added together. All of this thinking has already happened, so this time around I look at it, it is much easier for me to do that. But the more time you use at the beginning to decode it, the easier it becomes later. So you slow down at the beginning that you can speed up later again. Whereas usually you might try to memorize it, you might not know what to do with it, and if you don't really understand it, it just gets harder and harder as you go on, and at some point you just break and say, I'm probably not good at this. But yeah, this is just a technique, and I call it a cluster. I think, what did I call it in the stream? Cluster nodes. So the cluster techniques is a technique. There are several different techniques that are called clustering, and one of them is by a psychologist, I believe, with the family name Ricco, R-I-C-C-O. They had a way of brainstorming which looks sort of similar-ish to a mind map, but it's not quite the same thing. And there you would write a word, and then rather than having a topic in the center, and then you try for a mind map, you usually you group them together. Here you just said, okay, this word gives me this association, I write it down. Maybe the word gives me another association, I write it down. Then my mind wanders back to the first association, I get 2 more associations, I write them down. So you get a cluster of words. And here you also get a cluster. You have the formula or equation in the center. Then around that you cluster the first level of explanation, and you might cluster a second and a third, fourth, fifth, however many. And this is also a cluster. So this is why I call this clustering, cluster nodes, equation cluster. I don't know, something along those lines. Yeah, but if you do that, you are able to slowly decode that and really understand the formula and what it's trying to say. Maybe not everything right now, but hopefully enough to continue with the text, and then later, if you come back to it, when you come back to it, you think, oh, that's what it's trying to tell me, and you understand a little bit more and a little bit more, and over time, at some point it becomes second nature to you, and you just write it down like that and say, oh yeah, that's obvious, why don't you get it? It's so obvious. Okay, I don't think there's anybody on the stream. If there's anybody, now is your chance to ask a question. As always, If this is not the case, and I think it is not, then I will see you again next week. And let's see where this whole journey is going and how long I will continue this. Right now it works well for me. I'm not sure it provides a lot of value for you guys. Hopefully it does. If nothing else, it provides me with some clips that I can later showcase in some of the videos in a more condensed form. Okay, so as I said, I think there aren't any viewers. If there are, they at least don't have questions or don't ask them in the chat. Then I cut it here. It's already been more than 1 hour. I hope you found it useful, and if you did, please don't forget to give the like button a high 5. Consider subscribing if you haven't already, and until next time, keep thinking.